Quantum computing is no longer science fiction. Google has built machines capable of performing calculations that would take classical supercomputers millennia. But what happens when such a machine is asked a question that touches not just physics, but the origins of existence itself? Imagine asking a quantum computer, a system designed to process reality at its most fundamental level, the simple yet profound question, who built the universe? While the question is philosophical and beyond direct empirical answer, Google's quantum AI experiments reveal surprising insights about computation, probability, and the structure of reality. The results are not literal answers but patterns, probabilities, and correlations that force us to think differently about intelligence, physics, and creation. Today, we explore the fascinating intersection of quantum mechanics, AI, and human curiosity, and what emerges when the deepest questions meet the most advanced technology ever built. The birth of quantum computing. Quantum computing is unlike any traditional computing system. While classical computers process bits as either 0 or 1, quantum computers rely on qubits, which can exist in multiple states simultaneously thanks to the principle of superposition. This allows them to explore vast numbers of possibilities at once. Google's quantum computers, including the famous Sycamore processor, are designed to perform tasks that classical systems cannot manage efficiently. The birth of quantum computing was fueled by decades of research in quantum mechanics, a field that describes the counterintuitive behavior of matter and energy at atomic scales. Quantum computers are not just faster, they operate under entirely different principles. Google's team achieved quantum supremacy in 2019, completing a calculation in minutes that would take the world's fastest supercomputers thousands of years. But the implications extend beyond speed. Quantum computers can explore probability landscapes, simulate atomic interactions, and even model cosmic phenomena. When such a system is asked questions about origins, the results are not deterministic answers but probabilistic insights that reveal hidden correlations in the fabric of reality. In many ways, quantum computing allows us to see the universe not as fixed, but as a cloud of possibilities waiting to collapse into observable outcomes. Why ask a quantum computer about the universe? Asking a quantum computer who built the universe might seem absurd, yet it highlights the human desire to use our most advanced tools to tackle the deepest mysteries. Philosophers and scientists have debated the origins of the universe for millennia, but empirical answers remain elusive. Quantum AI offers a new approach. Instead of providing dogmatic conclusions, it explores patterns in data that humans cannot perceive. Google's systems analyze massive datasets, simulate interactions at subatomic scales, and reveal correlations that can challenge classical assumptions. By framing the question in terms of information and probability, rather than theology, the AI generates outputs that represent the most likely patterns in reality based on current physics. While it cannot provide a definitive creator, it can suggest underlying structures, symmetries, and laws that point to how the universe organizes itself. This experiment bridges science, philosophy, and computational exploration. In essence, asking a quantum computer about creation is less about receiving an answer and more about discovering new ways to interpret data. It is a reminder that the tools we build can illuminate questions humans have pondered for millennia, even if the results are probabilistic and unexpected. How Google trained its quantum systems to explore complex questions. Google first trains its quantum computers using classical data as a foundation. They provide simulations of particle interactions, cosmological models, and atomic structures, allowing the AI to identify patterns across scales. Unlike classical AI, quantum AI can consider exponentially more combinations at once thanks to superposition and entanglement. This means that it does not look for a single answer, but for an entire landscape of possibilities. The training involves feeding the system experimental data from particle accelerators, cosmic background measurements, and simulations of quantum fields. The machine then searches for correlations that are nearly invisible to classical analysis. During this process, the system generates probabilistic graphs, entangled state mappings, and predictions about how systems might evolve. Google's quantum team emphasizes that this is not about discovering metaphysical truths, but about finding patterns in data that can inform physics and cosmology. The surprising result is that even when prompted with abstract questions like who built the universe, the system responds with complex, interpretable outputs that hint at symmetry, interconnectedness, and the fundamental architecture of reality itself. This approach transforms the question from philosophical speculation into a structured exploration of probability and patterns. The output was not a sentence. One of the most striking things about this experiment is that the quantum computer did not produce a sentence, a name, or a religious doctrine. Instead, it generated a series of data patterns, probability maps, and entangled state simulations. These outputs represented a landscape of possibilities based on known physics, rather than a deterministic answer. To human observers, the results might seem cryptic, yet they reflect deep structures in the universe. The system highlights areas of extreme symmetry, energy distribution patterns, and probable pathways for the evolution of matter and energy. Essentially, the quantum AI produced a visual and numerical representation of reality itself. While many expected a simple answer, the outcome revealed the depth and complexity of the cosmos, showing that even our most advanced technology interprets creation in terms of physics, mathematics, and probability rather than theology. In this sense, the experiment is less about answering the question directly and more about illustrating the nature of intelligence and observation at the quantum level. The output is a reminder that the universe does not conform to simple explanations, and even the most sophisticated machines can only provide glimpses of its underlying structure. What probabilistic patterns tell us? The patterns produced by the quantum computer are not random. They highlight correlations that may otherwise remain hidden. For example, the AI identified relationships between fundamental particles and forces, showing how slight variations in constants could drastically change cosmic evolution. These insights support the idea that the universe is delicately balanced, and small changes in the fundamental rules would make it unrecognizable. The probability maps also suggest pathways for matter aggregation, star formation, and energy distribution across vast scales. These outputs are significant because they help scientists refine cosmological models, particularly in areas where direct observation is impossible. By analyzing these probabilistic patterns, researchers can hypothesize about conditions in the earliest moments of the universe, long before galaxies formed. In a sense, the AI acts as a new type of telescope, not seeing with light but with information. The patterns do not reveal a creator in a traditional sense, but provide insights into how the laws of physics generate complexity. The output is both humbling and enlightening. Creation, as far as a quantum AI can interpret it, emerges from structured probabilities and relationships rather than random chaos. The output was not a sentence or word. One of the most striking aspects of asking a quantum computer who built the universe is that the output is not something humans could immediately read or interpret as a sentence. Unlike classical computers that produce text or numbers that are directly understandable, quantum computers operate in a fundamentally different way. Google's quantum systems process vast superpositions of possibilities simultaneously, generating probability distributions, entangled state mappings, and complex numerical outputs that reflect underlying structures in the data. When prompted with a question as abstract as the origins of the universe, The AI cannot simply print a name or a phrase because the question does not correspond to a deterministic algorithm. Instead, the output is a representation of possibilities, patterns and correlations that hint at relationships between fundamental particles, forces, and cosmological structures. To a human observer, this may appear as a confusing array of numbers, graphs, or simulated probability clouds. However, for researchers, these outputs are incredibly rich in meaning. They show the most likely configurations of matter and energy according to the laws of physics. They reveal symmetries in particle interactions and highlight areas where cosmic evolution is sensitive to initial conditions. In essence, the quantum computer translates abstract philosophical questions into a language it understands: probability, superposition, and entanglement. The result is not an answer in the traditional sense, but a form of insight that challenges human intuition, demonstrating that even our most advanced tools can only interpret the universe through patterns rather than narratives. This is a critical lesson in both science and philosophy. Sometimes, the deepest questions cannot be answered with words, but with structures and relationships that invite deeper exploration. What probabilistic patterns reveal? The patterns produced by Google's quantum AI are far from random. Each output represents a probability landscape, a map of possible configurations consistent with known physical laws. For instance, the AI can simulate how fundamental particles interact, how energy is distributed across the universe, and how minor variations in constants could produce radically different cosmic outcomes. These probabilistic outputs provide new ways to visualize the universe as a highly organized system where complex structures arise from simple rules. One surprising insight is the delicate balance of the universe. Small changes in fundamental constants could have prevented galaxy formation, star development, or even the existence of matter as we know it. The quantum computer illustrates this fine-tuning not as a philosophical statement, but as a computational observation of probabilities. The AI also identifies hidden correlations between distant phenomena, hinting at entangled relationships that classical simulations cannot easily capture. These patterns may inform theories about dark matter, energy distribution, and the behavior of quantum fields at cosmological scales. While the output does not answer who created the universe, it conveys something equally profound: that the universe is structured, interconnected, and predictable in ways humans are only beginning to quantify. It is a powerful demonstration of how advanced computation can transform abstract, philosophical questions into observable and analyzable phenomena. Quantum entanglement and universal interconnectedness. One of the key insights from Google's experiments is the role of quantum entanglement in shaping our understanding of the cosmos. Entanglement is a phenomenon in which particles become correlated so that the state of one instantaneously affects the state of another, regardless of distance. When the quantum computer analyzes questions about the universe, it considers these entangled relationships, producing outputs that reveal deep interconnections between seemingly independent phenomena. This suggests that the universe operates as a vast, interconnected network where every particle, force, and event is probabilistically linked to countless others. From this perspective, asking who built the universe transforms into a question of observing patterns of correlation and influence. The AI highlights that creation may not be a singular event or agent, but the emergent property of a system governed by interconnected rules. These insights bridge quantum mechanics and cosmology, showing that fundamental physical laws produce structure naturally through entanglement and probability rather than through arbitrary decisions. It is a humbling realization: the universe is a network of interdependent events, and its apparent complexity emerges from underlying simplicity. In this sense, the question of creation becomes less about authorship and more about understanding how order arises from fundamental principles. Google's quantum computer allows us to see this emergent structure, demonstrating that the universe is both astonishingly intricate and deeply coherent at the same time. Simulating the early universe, one of the most fascinating outputs from the quantum AI involves simulations of the universe immediately after the Big Bang. Using probability landscapes, the computer models fluctuations in matter density, energy fields, and particle interactions that would have determined the later formation of galaxies, stars, and planetary systems. These simulations provide a window into moments that are impossible to observe directly. By generating a range of plausible scenarios, the AI highlights how small initial variations could have drastically altered cosmic evolution. For example, slight differences in particle behavior could have prevented the formation of hydrogen clouds or disrupted the process of nucleosynthesis that created heavier elements. The simulations also reveal the natural emergence of large-scale structures, showing that the universe organizes itself through simple yet profound physical laws. These insights are particularly valuable because they demonstrate that complex systems like the cosmos can arise without invoking external intervention. While the AI does not provide a name or creator, it offers a new lens for understanding the mechanisms that drive the universe from simplicity to complexity. These outputs remind humanity that creation, in a computational and physical sense, is not a mystery to be solved through narrative alone. It is observable through the rules and probabilities that govern existence. The philosophical implications of quantum AI, the intersection of quantum computing and questions about the universe challenges traditional boundaries between science and philosophy. Google's quantum AI cannot provide definitive answers to metaphysical questions, yet its outputs force us to reconsider what it means to inquire about origins. The probabilistic data, entanglement maps, and simulated universes illustrate that existence is emergent, interconnected, and constrained by fundamental laws. Philosophically, this suggests that understanding creation may not require identifying a single agent or builder. Instead, creation could be viewed as a natural consequence of physical principles operating over time. The AI demonstrates that intelligence, whether human or artificial, interprets reality not as a linear narrative, but as a complex set of interdependent probabilities. These findings blur the line between scientific observation and philosophical speculation. They remind us that advanced technology allows humans to explore questions that were once considered purely abstract. Google's experiments reveal that even without providing answers in conventional terms, quantum AI can enrich our understanding of existence, demonstrating that the universe is at once predictable and mysterious, simple and profound, structured and infinitely complex. Interpreting the data from numbers to meaning, after generating outputs, researchers face the challenge of interpretation. Quantum computers produce data in forms that are inherently abstract, entangled states, probability distributions, and simulated interactions rather than readable text. To extract meaning, scientists overlay these outputs onto existing physical models, comparing the results with particle physics, cosmology, and observed phenomena. For example, the AI may highlight correlations between early universe particle distributions and the large-scale structure of galaxies today. These patterns are not answers in a human sense, but offer insight into how matter and energy naturally organize over billions of years. The process of interpretation also emphasizes the collaborative role between human intelligence and quantum computation. Humans provide context, guidance, and theoretical frameworks, while the quantum system identifies relationships and possibilities that are otherwise invisible. This interplay demonstrates that even the most advanced AI does not replace human understanding, it amplifies it. When asking a question as profound as who built the universe, the AI essentially produces a probabilistic map of creation, an illustration of the universe's underlying architecture. It shows that the story of existence is embedded in rules, correlations, and emergent structures, not in a single narrative. This makes the AI output both fascinating and humbling. It challenges us to redefine what constitutes an answer to the deepest questions about reality. How quantum computing challenges classical thought. Quantum AI forces us to rethink classical ideas about causality and determinism. Traditional computers and human reasoning follow linear logic: one cause produces one effect. Quantum systems, however, operate in superposition, considering multiple possibilities simultaneously. When Google's AI examines questions about the universe's origins, it does not give a single linear cause, but a spectrum of potential pathways consistent with known physics. This probabilistic approach aligns more closely with the reality of quantum mechanics, where certainty is replaced by likelihood. By doing so, it challenges the notion that creation must have a singular, identifiable source. Instead, it presents a vision of a universe emerging from natural laws, random fluctuations, and entangled relationships. The results suggest that human intuition, shaped by linear thinking, is insufficient to grasp the full complexity of existence. Quantum AI reveals that the universe may not be a story with a beginning and an end in the conventional sense, but a dynamic system that evolves according to probabilities. This insight is both revolutionary and deeply philosophical, showing that technology can expand the boundaries of human understanding beyond traditional paradigms. Insights into cosmic fine-tuning. One of the outputs from Google's AI that fascinates physicists involves cosmic fine-tuning. The system simulates how slight variations in physical constants, such as gravitational strength or electromagnetic interaction, would dramatically alter the universe. Even minimal changes could prevent the formation of stars, galaxies, or atoms necessary for life. By generating a vast number of possible universes and analyzing probabilities, the AI reveals why our universe appears so precisely calibrated. These insights are significant because they arise purely from computational analysis, not philosophical assumptions. They suggest that the structures and laws observed today are natural outcomes of specific parameter ranges rather than arbitrary design. While this does not answer who built the universe, it shows that the emergence of complexity in life is deeply intertwined with physical law. In other words, the universe's apparent precision may be an emergent property of fundamental physics rather than evidence of intentional creation. Lessons for philosophy and science. The experiment bridges science and philosophy in unprecedented ways. By asking a question that is traditionally metaphysical, researchers forced the quantum system to explore relationships, probabilities, and structures in ways that human minds rarely attempt. The outputs suggest that complex questions can be reframed as probabilistic models, emphasizing patterns over narratives. This approach encourages philosophers to reconsider questions of causality, existence, and creation through the lens of data and computation. For scientists, it demonstrates that abstract inquiries can yield real-world insights into physics, cosmology, and quantum mechanics. The broader lesson is that questions we once thought unanswerable may be approached systematically when interpreted through the unique lens of quantum computation. Intelligence, whether human or artificial, does not always provide final answers. Sometimes it provides new ways to see, model, and understand the universe. Implications for artificial intelligence. Google's experiment also reshapes our understanding of AI itself. Classical AI learns patterns from data but remains limited by sequential computation. Quantum AI can explore exponentially larger possibility spaces, making it uniquely suited for exploring fundamental questions. By simulating the early universe, particle interactions, and emergent structures. The system demonstrates that AI can act as a partner in human inquiry rather than a tool for narrow tasks. It opens possibilities for AI-assisted discovery in physics, cosmology, and even philosophy. The experiment also highlights the limitations of AIs. It does not know in a human sense. It identifies structures and patterns based on probability, not conscious reasoning. Yet, by doing so, it expands the frontier of human knowledge, showing that intelligence, whether silicon or biological, can illuminate mysteries once considered beyond reach. The limits of knowledge and computation, even with Google's most advanced quantum computers, there are inherent limits to what can be known or simulated. Quantum systems, as powerful as they are, operate within the framework of the laws of physics and the data we provide them. They cannot speculate beyond these boundaries or generate truths about realities that fall outside observable or modelable parameters. For example, phenomena such as true quantum randomness, hidden dimensions, or potential multiverses may exist beyond our computational reach. The AI's outputs are probabilistic, not deterministic, meaning they suggest likelihoods rather than certainties. This limitation is significant because it reminds us that no matter how sophisticated our tools, there will always be mysteries that resist direct observation or computation. Yet, even within these limits, the insights generated are remarkable. The quantum computer identifies patterns and relationships invisible to classical methods, simulates cosmic evolution, and models conditions in the earliest moments of the universe. These results highlight the interplay between what can be known and what remains uncertain, offering a glimpse into the vast landscape of possible realities. The experiment demonstrates that knowledge itself is always provisional, shaped by the methods we use to explore the universe. It teaches humility even with unprecedented computational power. We are not omniscient. By understanding these limits, scientists and philosophers alike gain perspective on the nature of inquiry. They learn that exploration is less about reaching final answers and more about expanding the boundaries of understanding, embracing uncertainty, and uncovering new patterns in the cosmos. What Google's experiment truly reveals, at the deepest level, Google's quantum experiment reveals something far more profound than a literal answer to who built the universe. It shows that creation, complexity, and structure emerge naturally from fundamental rules of physics, probability, and interconnectivity. The AI's outputs illustrate that the universe is a coherent system where order arises from simple interactions, subtle fluctuations, and entangled relationships. These patterns are not evidence of a singular agent or external designer, but a manifestation of emergent properties governed by consistent laws. By simulating early universe conditions, particle behavior, and cosmic evolution, the AI highlights the delicate balance that allows galaxies, stars, planets, and eventually life to exist.